Suppose we say I'm thinking of two numbers, 5 and 3, and their sum is 8. We would write that as 5 plus 3 equals 8. But suppose I say I'm thinking of two numbers and their sum is 8. Well, we don't know what those numbers are, so we can use variables. X plus y equals 8. We could say a plus b equals 8. S plus t equals 8. We can use any pair of variables that we want. And these could represent 8 and 0, 4 and 4, 10 and negative 2, pi and 8 minus pi. We don't know. But we want to make sure that we're using the right terminology. So when we have, let's move that over, a variable, it's generally a letter that's standing in for an unknown number. So X, Y, T, A, B, S, R. Integers are going to be our counting numbers, and they're negatives. So minus negative numbers counting up to negative 3, negative 2, negative 1, 0, 1, 2, 3. And notice that I am including the integers in the order that they would appear on the number line. I don't start at 0 and then 1 and then negative 1 and then 2 and then negative 2. I will always list integers in increasing order. Next, positive numbers. Positive numbers are just numbers that are greater than 0. Negative numbers, numbers that are less than 0. 0 itself is neither positive nor negative. Now, sometimes we will want numbers that are positive and equal to 0. So we will call these non-negative numbers. Numbers that are positive, greater than 0, together with 0. So these are all numbers greater than or equal to 0. So now that we have our numbers, we can do things with them. So we have the standard operations. So we can add. 6 plus 2 equals 8. We can subtract. We can have 6 minus 2 equals 8. We can multiply. 6 times 2 equals 12. We can divide. 6 divided by 2, or we can write it as a fraction, 6 over 2 equals 3. Or we can use exponents. 6 squared equals 36. So these are the basic operations. With these operations, when we're given or we're trying to evaluate a string of numbers put together with operations, we need to know the order of operations. So there are a couple different mnemonic devices. The most common one that I've heard of is PEMDAS, PEMDAS, and that stands for parentheses. We can have exponents. So we evaluate all parentheses, then we evaluate all exponents, then we evaluate multiplication and division, just from left to right. We may divide before we multiply, that's fine. And then finally we have addition and subtraction from left to right. So we will use the order of operations to evaluate the following expressions. We have 20 minus 3 times 2 squared. So there's no parentheses. So we evaluate exponents. So 20 minus 3 times 4. We multiply 20 minus 12, which equals 8. For the next expression, we have 20 minus 3 times 2 squared. So now we have a parentheses. So we evaluate the parentheses first. So 20 minus 3 times 2 is 6 squared, which equals 20 minus 36, which equals negative 16. We can have the entire 20 minus 3 times 2 inside parentheses. So we start inside our parentheses and we follow the rest of the order of operations. So we do not subtract first, we multiply first. So inside of our parentheses we have 20 minus 6, that quantity squared. We have 14 squared, which is 196. And then our final expression, we evaluate parentheses. So we have 17 times 2 squared. We evaluate exponents. So 17 times 4. 17 times 4 is 17 times 2, which is 34, times 2, which is 68. So in this course, we will be using certain terminology. So to make sure that we all know that we're talking about the same values. So a rational number. Let's move this over. So a rational number is when you divide one integer by another integer. An irrational number is when a number cannot be expressed as a fraction of integers. So examples are the square root of 2 or pi. Real numbers are all rational and irrational numbers combined. So, and then the last thing are imaginary and complex numbers. Within this class, we are not going to consider imaginary or complex numbers. So when we take a square root, we only want to take the square root of non-negative numbers. So we will not use imaginary or complex numbers in this course. So now that we have our operations, we're going to look at a couple different properties of some of these operations. So the first question is, how would you solve 98 plus 99 in your head? You're not allowed to use paper, you're not allowed to use a calculator. And yes, we can do 9 plus 8 is 17, so we end up with a 7 in the ones, and then 9 plus 1 is 10, plus another 9 is 19, so we have 19 tens plus 7 is 197. Yes, we can do that in our head. But there's an easier way. We can write 98 as 100 minus 2, and we can add that to 99, which is 100 minus 1. Well, I can just add my 200s. Okay, I can add my 200s and then subtract off my 2 and my 1. So I can to get 200 minus 3, which equals 197. And so, imagining the 98 stacked on top of the 99 and doing vertical addition isn't too bad in this problem. But this method where I rewrite 98 as 100 minus 2 and 99 as 100 minus 1, and then I rewrite my terms, the numbers that I'm adding, to make it easier to add and subtract. This method would be a lot easier if we're adding 98 plus 97 plus 196 plus 299. If we need to add those four numbers, stacking them and keeping track of what goes in the ones column, what goes in the twos column, the tens column, that's just a lot more work. But I can write this as 100 minus 2 plus 100 minus 3 plus 200 minus 4 plus 300 minus 1. Right here we have 300, 400, 500, 600, 700 minus 2 minus 3, which is minus 5, minus 4 more is minus 9, minus 1 more is minus 10. 700 minus 10 is 690. And that's a lot easier than stacking and trying to keep track in our heads of what goes in what column. Well, this was possible only because I was able to switch these two numbers. I could switch the minus 2 and the plus 10. Right over here, I start with 100 and I end by subtracting 1, but I switch this blue minus 2 and the green plus 100. Those two numbers move, they switch places, they commute. So this is called the commutative law of addition. And that basically means I can switch the order. Oops, that's not what I want to do. That means that I can switch the order of addition. I can add A plus B, or I can add B plus A. So addition is commutative, so is multiplication. Move that out. I can multiply A times B, or I can multiply B times A. Either way, we get the same value. So addition and multiplication are commutative. Is subtraction commutative? That is, generally speaking, is A minus B going to equal B minus A? Well, generally speaking, no. 5 minus 3 is not going to equal 3 minus 5. Now there is an exception. If A equals B, then A minus B will equal B minus A. And then, is division commutative? Is A divided by B equal to B minus A? Generally speaking, no. Let's rewrite that a little nicer. So no, these operations are not generally commutative. Now, for division, if A equals B, then A divided by B will equal B divided by A, which will equal 1. Or if A equals negative B, if you divide them, you get negative 1. So another way we could solve 98 plus 99 in our head without using paper is I could think, hey, 99 is really close to 100. Now if I take 1 away from 98 and add it to 99, that'll make my addition a lot easier. So I can rewrite 98 as 97 plus 1 and add that to 99. Then I can add the 1 plus 99 first to make 97 plus 100, which equals 197. Right? The same answer we got back here, 197, just a different method to get there. So the question is, what property allows this one to stop associating with the 97 first and associate with the 99 first? This is called the associative law of addition. And it just means that I can add, if I'm adding numbers, I can add them in whatever order I want. So I can add A plus B first and then add C. I could add B plus C first and then add A. The commutative law of addition with this actually tells me I can add A and C first and then add B. If I'm adding numbers, I can add them in whatever order I want. Whoops. So is multiplication associative? Yes. I can multiply B times C and then multiply by A, or we can multiply A by B and then multiply by C. That's fine. We can multiply in whatever order we want. Is subtraction associative? Well, no. Generally speaking, that's a little... generally speaking, we can't switch the order of subtraction. We can't subtract B minus C and then take A minus B minus C. That is not the same thing as A minus B and then subtracting off C. And then the final question, is division associative? No, same reason for subtraction. If I divide B by C and then take A divided by that, I will not get the same value if I divide A by B and then divide by C. And then one more question. How would you solve 32 times 102 in your head with no paper or a calculator? Well, we can see that we can do 32 times 100 and then 32 times 2. So we get 32 times 100 equals 3200. 32 times 2 is just 64. So 32 times 102 is going to equal 3200 plus 64 is 3264. So yes, we can keep track of those numbers in our head. I'm writing them down for you to see, but we could do that without writing it down. This is called the distributive property because we distribute the A into our parentheses. So A times B plus A times C. A plus B, A times B plus A times C. So we will use this distributive property both ways. We will use it to distribute. We will be given A times a sum, which equals A times B plus A times C, or we will use it to factor. We'll be given a sum, and we'll notice that we have each term has a common factor A, and we can factor that A out to make A times the quantity of B plus C. So we can do it both ways. Now, I want to go back to the commutative law real quick. So something to note is that addition and multiplication are commutative, subtraction and division are not. But if we rewrite subtraction as adding a negative, so we can write 5 minus 3 equals 5 plus negative 3. Now we can commute these values. We can write that as minus 3 plus 5. This is not 3 minus 5. We are commuting numbers that are being added, not subtracted. So in this sense, we can commute, which is what we used up here to commute the minus 2 with the plus 100. So our final step is I want to evaluate a couple of expressions. So we want to evaluate 5 divided by 4 times 4 divided by 6 times 6 divided by 5 times 10 divided by 5. So we can simplify. We can cancel. We have a 4 in the numerator and a 4 in the denominator. 4 divided by 4 is 1. We have a 6 in the numerator and a 6 in the denominator. 6 divided by 6 is 1. 5 in the numerator, 5 in the denominator. 5 divided by 5 is 1. So we're just left with 10 divided by 5, which equals 2. So now we want to simplify 7 times 3 divided by 7. Well, I've got a 7 in my numerator, a 7 in my denominator. I can cancel those and get 3. Now I want to simplify 7 plus 3 divided by 7. Well, hey, I've got a 7 in my numerator, I've got a 7 in my denominator. I can cancel those and get 3. No, this is not what we do. This is wrong. When we can only cancel like this when we are multiplying. So up here we have 7 times 3. So if I take 3, multiply by 7, and then divide by 7, we get back to 3. But here I am adding and then dividing. This is equal to 10 over 7. And then our last expression. Oh, wow, that's a lot of adding and subtracting, and I don't want to do all that. And I don't have to do all that. I can recognize that every term in the numerator is a multiple of 9. So we can factor out a 9 in the numerator. So if I factor a 9 out of 81, we're left with 9. If we factor a 9 out of 72, we're left with 8. If we factor a 9 out of 63, we're left with 7. And if we factor a 9 out of 54, we're left with 6. So all of this divided by 9, Well, now we can cancel out the 9s. We're left with, well, I don't want to necessarily have to add 9 and 8 and then subtract 7 and 6. I can rewrite this as 9 minus 7 plus 8 minus 6. 9 minus 7 is 2. 8 minus 6 is 2. So that answer is 4. Now, 9 plus 8 is 17. Minus 7 is 10. Minus 6 is 4. It's not that hard, but this method, I don't have to deal with big numbers. I can make my numbers smaller before I make them bigger. Either way's fine. They're both valid and accurate. Two different solutions to get to the same answer.